Hello, everyone. Just before the technical talk and the panelists start, just reminder, tonight we have a social event offsite in the Estación de Francia. How to get there? Well, first, you have to have 2 single train tickets in your batch, remember? I mean, you can go by walk also, eh? It's a long distance, but anyway. It's very easy to go there. You have to go down to the train station, you take the RISC-V train, and in 20 minutes, 2 stops, you will be in the Estación de Francia. Then once you get there, to enter into the restaurant, basically, you have 1 ticket in your batch also, remember? So the batch is like this. You have it in this way, so easy to find. And that's all. So we start at 8. You can be there earlier or a little bit late. We have a welcome drink to wait everybody. And after that, just have fun and relax a bit, okay? So with that, we're gonna start with the technical talks. Thank you. I hope you're enjoying.
So hello, I'm pleased to introduce to you Jeremy Bennett. He is Chief Executive of Embecosm. He's also chair of the Software Task Group of the OpenHW Group and the author of the standard textbook, Introduction to Compiling Techniques. So his talk is about the Core 5 software ecosystem, 10 lessons learned from developing vendor-specific compiler toolchains. Jeremy, the floor is yours.
Thank you. Good afternoon. Thank you all very much. And you wouldn't believe the coaching session that went on beforehand on how to pronounce my company's name. There's 2 logos on this because I'm speaking both with my Embecosm hat on and with my Open Hardware Group Core 5 hat on. So let's just quickly summarize. You heard from Rick O'Connor yesterday about the Open Hardware Group, a collection of 100 and something entities, all working to produce commercial grade silicon IP and software. And the brand name, or the logo we use, is Core 5 for the series of cores, a series of 32 and 64-bit RISC-V cores from the very smallest to the very largest. As part of that, we've developed GCC and LLVM toolchains. It's been a collaborative effort. Engineers from the University of Tübingen, from the University of Bologna, from PLCT in China, and my own team from Embecosm, and with support from companies like Silicon Labs and Dolphin Design. And we've been doing this for some time, and I thought it would be fun to share some of the lessons learned. This did start out as 3 lessons learned, and it grew as I wrote it, so it's 10 lessons learned. So Embecosm's a software consultancy. You know us best for compiler tool chains. A lot of it's pre-silicon, so we develop processor models. It ties into operating system bring up, so we're doing that. And I'm not going to talk about it today, but if anyone wants to know about Bayesian inference, AI and ML, I'll be very happy to talk to you about that, because that's something else we do. We've got R&D centers in Southampton, Paris, and Nuremberg. And just to get it out here, like everyone else, we are hiring because we cannot get enough compiler engineers. So what are the 10 lessons? First of all, you tend to develop on your own branch of the main tree. Rebase often. RISC-V is very actively developed, and rebasing from an old mirror is laborious. And you always want to be developing against the latest developments anyway. So ideally, rebase every month. But it's a big cost. It's probably an engineer taking a week to do that with the amount of churn there is. Second 2, avoid committees. I'm not going to go in for a simple, because committees are essential. It's how we get consensus. They do valuable work. A lot of people give up their time. But that time is important, is the critical thing. If your development is going to be held up waiting for a committee, then that's a problem. So try and work with what we've got rather than things. And we had a simple thing which took 4 months to resolve for the simple reason the committee was waiting on me and I was waiting on the committee, and neither of us understood this. So they try and use what's there. Don't wait for stuff to go through committee because that may take a long time. Something we also learned, this is somewhere where RISC-V is steering anyway. You're allowed to have multiple versions of ISA extensions. You can put, P1, 1P0 on the end or 2P0 to indicate different versions. And Core 5 has been around long enough, we've actually got multiple versions of the instruction encodings, the original ones from Pulp and the new ones that are RISC-V compliant. So we thought, well, we'll support both versions. It's not actually much done, and what we discovered was that particularly in the GNU assembler, actually the infrastructure isn't there. And not only is the infrastructure not there, it isn't a trivial job to put it in there. It's not a deliberate thing, it's no one's ever needed it, and it's sort of got a bit rotted. And we took the simple solution saying we don't really care about the old encodings because that's not what people are making silicon out of. So we've just abandoned the old encodings and just supporting a single version. If you plan for that, you won't be disappointed. Another one, this is another accidental one. Use lowercase assembler mnemonics. Our assembler mnemonics actually a mixed case. The suffixes in uppercase tell you something about how these instructions are working. The GNU assembler assumes lowercase, and this is only a GNU problem, assumes that assembler mnemonics for RISC-V are in lowercase. It's a RISC-V GNU problem. I can't say it's deliberate, it's baked in throughout all the code, and it comes into another category of, yes, we could fix it, but it's too much trouble. So we decided to change the mnemonics and have them all lowercase. Not a problem for LLVM, because LLVM has the automated concept of case insensitivity in the assembler. This is an important one. So RISC-V thought ahead and thought, in the ELF spec, you've got 256 possible relocations. The top 64 we'll leave aside for vendors. Of course, we know how many vendors are. That's well under one relocation per vendor. And of course, you're likely to need more than one custom relocation. Now, we know how to solve that problem. We've known it for 3 years. We're going to add a new 32-bit standard RISC-V relocation, which will identify the vendor. And then you'll put that and your custom relocation. It will say, of those 64 vendor-specific relocations, use the meaning associated with this customer. But that's a good example of my second idea, the committee problem. We've still got to get that through the committee. The committee is quite reasonably asking for a reference implementation, which my team are working on, so that you can check it really works before we do it. That's an important aspect we found was holding us up. Built-in functions. RISC-V loves built-in functions. It's tempting to just slavishly do a built-in function for every instruction. They're there to help the software user. They're not there to mimic the hardware. So think about what you want to use your built-in functions for. So for example, Core 5 has its SIMD has 4 shuffle instructions. Why does it have 4 shuffle instructions? Because there are 256 shuffles you can do, but there's only a 6-bit constant, so you divide it into 4 instructions, each with 64 of the ones you can do. Don't make 4 built-ins. We have a single built-in. It looks at the constant and works out which of the 4 instructions to generate. And that leads into the second thing, is not everything needs built-ins. Built-ins are not good. There's no point in having a built-in for a single branch instruction. And quite often, if you've got a different addressing mode for a memory operation, again, it doesn't fit well in a built-in. You want the compiler to generate that directly so you get the full value of it. Okay? So think about your built-ins. And we thought, oh, we'll just do the built-ins. We ended up within Core 5, actually with a 3 or 4 month process where we ended up defining our built-ins, reviewing them, ratifying them, checking them, trying them again, testing them out, and eventually settling down and think it's not actually as easy as you think, defining a built-in. This ties in with my first thing, maintaining that out-of-tree fork of things. Do it all upstream. Upstream early and upstream often. We got that one very, very wrong. We should have started upstreaming the Core 5 stuff 2 years ago. We're about to start doing it. You become part of the upstream code base. You don't have to keep on rebasing to keep up. You may be depending on critical functionality upstream. Unless you're upstream as well, there's no reason why someone couldn't take that critical functionality away and then you're high and dry. Okay? So get yourself upstream as quick as you can. One of the reasons we were holding back is because we need the vendor-specific relocations, but we need it for 1 extension out of 8 extensions we're doing. Let's put the other 7 up, and we'll worry about waiting for the last one a bit later. And it's a long tradition. Long before RISC-V, GCC and LLVM have accepted vendor-specific relocations, so vendor-specific variants. So, you know, it's easily done. That's why your target triple has a vendor field to say which vendor you are. So it's not a new topic there. This is one that you have to learn, and we see quite a lot of submissions upstream that don't know this one, is use the upstream conventions. You may know the best possible way to lay out your code, but if it isn't what your upstream tool wants, you won't have your patches accepted, okay? So stick to the coding style of upstream, even if it's not your favored way of laying out code, okay? And there's a tool called Clang Format, and Clang Format will lay your code out according to convention. And it's actually the way to lay out your GNU code as well, because you can tell it to lay out in the GNU style as well. So use Clang Format and have it as a commit hook, you know. But it's not just code style, it's patch format conventions, submission and review process. Learn to work with that. And even when you're working in your out-of-tree fork, follow those same conventions so when you come to upstream, you won't have a lot of pain. Okay? And the last of my 10 lessons is use proving grounds. What do I mean by that? You will hear us say a lot, and I want to say is you have to work in your upstream community, and that's absolutely true. If you're doing a GCC compiler, work with the GCC community. If you're doing an LLVM compiler, work with the LLVM community. That's where the bulk of the work should be done. But particularly early on, you also have to engage with your target community. And in this case, it's RISC-V. In this case, it's specifically Open Hardware Group. And it allows you to take a target-specific view of the world, which when you're working out the early stuff is really useful. Allows you to gather consortia together, the team we've got from those various companies and universities to work together. What it also allowed us to do was it allowed us to set up a smaller group just to get to know. There aren't enough compiler engineers there, and what we learned by accident is we are a training ground for new compiler engineers. A lot of the engineers doing this work are some of my graduates, some of the students at PLCT, students at various universities, along with some very experienced engineers, particularly from Embecosm. And we've ended up meeting for half an hour for LLVM and half an hour for GCC every Friday. There are open meetings, any of you can attend, where we review patches. And that's how we teach the new engineers. It's a smaller community. It's not like doing it in the full glare of the whole upstream. And it's turned out to be a good way of bringing on some young engineers. So those are my 10 lessons. I hope those are useful to you, give you some insight. Thank you very much. And I think we've got a few minutes for questions.
So are there any questions? Any other lessons that you would want to know about?
Stunned silence.
How do you convince the students to go to the lessons and to the compiler adventure?
Well, if you like compilers, you end up loving them. I do compilers. It's been an obsession with me since, well, a long time ago. And that's what motivates most people. There is a secondary motivation. It is a fabulously well-paid discipline of software engineering, so there is a big incentive to learn this stuff. And compiling is really hard. It's not taught at most universities because there aren't people who can teach it. And as a consequence, there aren't many compiler engineers. I did a study for the British government a few years ago. I reckon of true professionals, people who you can say, I need a new compiler for my architecture, and I want it to always work and always be good code and pass all the tests. There's, for GCC and LLVM each, between 20 and 50 people in the world of that caliber. Now, that's really valuable. You know, if they were lawyers, they'd be earning 5 million a year. They don't earn quite that much, but it's a well-paid discipline, and that's a motivator as well. But it's really, we do it because we love it. Lots of money's a bonus.
Okay. Christian, the question?
Do you see MLIR taking off, and if so, which kind of domain?
So do we see MLIR taking off? I was at Euro LLVM a couple of weeks ago. You couldn't move for MLIR talks. I think there's a lot of discussion because people see the value of MLIR, and I should say I'm more of a GNU person. I'm not an LLVM expert. But you are seeing it. I think particularly some of the front-end domains. So if you look at Flang and the potential to move the Flang IR to become a variant of MLIR, at some stage the whole LLVM infrastructure will have to move to being more MLIR-centric. But LLVM at the moment is still using the original IR. So I think it's an open question. A lot of people are talking about it. It will settle over the coming years as to where it becomes important.
We have time for another question.
Do you see runtime compilation, some stuff you places for that into the RISC-V environment?
Runtime compilation has its use. Yeah, I mean, we're not doing any work on that. It hasn't come up yet, but it will come in time. For certain applications, it's really useful. And of course, LLVM was very much created with runtime compilation in mind. It's a bit hard. You can do it with GCC, but GCC JIT is a bit tricky. Yeah. Okay. All right, I think we're done.
Okay, thank you.
Thank you all
very
very
much,
much.
Jeremy.